Okay, let's get started. Good morning, good afternoon, and good night, everyone. My name is Jima. I'm a machine learning lead at University Health Network. Welcome to join this webinar on foundation models for interactive and text-guided 3D biomedical image segmentation. There are two major purposes for this webinar. First, we would like to provide a general introduction of the competition, especially for its task settings and datasets. And second, we also invite state-of-the-art algorithm developers in this field to share their amazing solutions. Oops. Segmentation plays an important role in various clinical and biological applications, such as surgery planning in CT scans and cancer microenvironment analysis with microscopic images. Actually, segmentation is not a new task. It has a long history with half a century. We have seen three major paradigm shifts from heuristic methods like thresholding and region going to model-based methods in 1980s, such as variational models. More recently, we have moved to deep learning-based specialist models from 2015 to 2022 with architectures like FCN and UNet. And since 2023, we have been seeing the rise of foundation models like segment anything models. SEM has revolutionized the prompt segmentation with a unified task, a modular network, and a large-scale dataset, achieving strong generalization ability across various domains. However, many studies have shown that SEM failed to segment medical images. This is not surprising because SEM was trained on natural images. Based on SEM, we built MedSEM by fine-tuning the SEM model on a large and diverse medical image dataset. However, the models still has high computational demand. To address this issue, we built a large SEM and organized this computation in CVPR 2024 MedSEM on laptop to accelerate the development of efficient medical SEM models. This is our summary paper, and so based on the results, it can be found that many models achieved great performance on 2D segmentation tasks, but 3D segmentation accuracy lagged behind. Lastly, we released the MedSem tool for 3D medical image and video segmentation with broad integration, as well as large-scale US studies. Although the model has better performance for 3D segmentation than previous version, and can significantly reduce the human annotation cost. But SEM-based models still have two essential limitations. First, the model architecture is designed with 2D image encoder, which cannot capture the 3D context. And second, it is not suitable for 3D interactive segmentation. Fortunately, there are lots of exciting progresses for 3D interactive segmentation, such as SEMAT 3D, SegVL, Vista 3D, ProtoSem 3D, and recent Interactive. In addition, text-guided segmentation is another exciting direction because text is a more flexible prompt. Those progresses motivated us to further extend the CVPR 2024 task to this year's 3D interactive and text-guided segmentation, aiming to push the boundary by gathering community efforts. Let me start with a brief introduction of the interactive 3D segmentation task. So we provide the input contains 3D image and one 3D box prompt and 5-point prompts. For the box prompt, it is defined as the middle slice 2D box plus top and bottom slice index in a closed interval. Here are the case of the box prompt. The motivation is that users can easily draw a 2D box in various image viewers, such as 3D slides, and it is also easier to specify the top slice and the bottom slice of the target. However, it is not that user-friendly to directly draw the 3D bounding box. For the 5-point prompts, they are iteratively generated by comparing and ground truth with segmentation mask. The expected output is the segmented mask for its point prompt during iteration. Here we have three important remarks. First, the series 3D box may not cover the complete object. So this is expected since it was generated by first drawing a 2D box on the middle slice, followed by specifying the top slice and the bottom slice. And the second, box prompter is optional to use, which means you can directly ignore the box prompt and start with the point prompt. And the segmentation of the initial box prompt is not evaluated during ranking. And third, it should be noted that some objects don't have box prompts, for example, values. The reason is that for those kind of segmentation objects, box is obviously not a good prompt. Well, instead, point is a better prompt. The training set contains four modalities by aggregating over 70 publicly available datasets. Since not every research group can afford the computing to process such large data sets, we set a core set track in addition to the normal four training set track. So in other words, participants can participate either of the tracks, and they can. So if the computation is a limitation, they can develop their own core set selection methods to select 10% of the training set for model development. We also collaborated with all participants to create a dataset, a public and accessible dataset list with over 100 public datasets. We randomly select 10% cases as the validation set. For the testing set, we will also cover all those modalities, and we are building partnership with global medical centers and other MICAI segmentation challenges, aiming to create a hidden testing set where none of the case is publicly available. We have applied data pre-processing to reduce the variance. For CT images, we first adjust the CT value to proper window level and width, followed by rescaling the values to 0 to 255. For other modalities such as MR, PET, ultrasound, we apply cutoff with 0.5 and 99.5 percentiles of foreground voxels before the rescaling. If the original intensity range of the images is already in this range, we didn't apply any intensity pre-processing. For the labels, we exclude the objects with less than 100 voxels. The reason is that for those kind of segmentation targets, the main challenge is automatic detection instead of interactive segmentation. And the second, we also convert latent labels to instance labels, allowing to generate latent-wise prompt. Furthermore, to reduce the dataset size, only labeled region of interest is saved. For data format, each case is saved as a OpenPDF file with various case. For example, for training set, the case include image, ground truth, and spacing. For validation and or testing set, the case include images, box, spacing, and text prompt. It should be noted that the box prompt is optional for some targets such as vessels and multi-component brain tumor lesions. We are still open for registering new publicly available training set. It is still today. So if you found that here is the current complete list, you can find the link on the dataset page on the committee's homepage. It should be noted that only the listed public datasets can be used for this challenge. The goal is to make sure every participant can access a same set of public datasets. We will finalize the dataset pre-processing by the end of this week, since some participants made some submit some new uh, public data sets with license permission for redistribution. We will pre-process them and add it to the current training set. But for some for the data sets that don't allow to redistribute, we have released the pre-processing code. So we recommend the participants to pre-process them locally and add them to the training set. After that, we will upload the dataset to Hugging Face for which is more user-friendly to download. At the same time, we are maintaining this community-driven dataset list. In addition to the basic dataset meta information, we also provide the data download link, paper associated paper links, and bibliotext. So welcome to add new dataset if you found that the public dataset is missed in this list. So finally, I'd like to thank all data contributors and baseline contributors. And I also would like to acknowledge Zhongzheng and Fabian for their valuable feedback on the dataset and challenge design. Last but not least, thank all participants very much. Your participation and feedback are extremely important to us.